Hello, this video is about Nobel Prize in Physics, 1917, awarded to Charles Grover Barkla for his discovery of the characteristic Röntgen radiation of the elements, another important step in the development of X-ray spectroscopy. And here you see the original photograph made by Röntgen in 1895, when he discovered the Röntgen rays. Here you see the equipment he used. This is a later experiment, as you can see. And here you see the equipment used by Barkla and some of his results. Okay, then the Nobel Prize lecture given by Barkla, named Characteristic Röntgen Radiation, summarized by me. Today, as about the results of my own experiments which have a bearing on the quantum theory of radiation and of the evidence for another series of characteristic radiation, the J series. 1. The quantum theory of radiation, phenomena of scattering. The results of the experiments briefly summarized. When X-ray coming from an X-ray tube travel through matter, this matter itself becomes a source of secondary radiation. This secondary radiation is usually scattered around the primary beam and varies in intensity and is slightly polarized in relation to the primary beam. The scattered radiation that is at right angles with the primary radiation is highly polarized. The variation in intensity of the scattered radiation with direction relative to the axis of the primary radiation agrees with the theoretical distribution given by the equation I0 is In divided by 2 times between brackets 1 plus cosinus squared phi. Here you can see what is meant by that. I0 is the intensity at an angle, In was the original intensity, phi is the angle by the primary and secondary beam. This equation is derived from orthodox electromagnetic wave theory. The deviation of this equation depends essentially on the steady variations with direction, not of a number of invisible entities, but of the energy density around a single radiation charge, in this case an electron. Neither atoms, molecules or gaseous ions were the scattering units, but that these were the constituent electrons in matters, and that in general the number of electrons per atom for light atoms at any rate, proportional to the atomic weight, hydrogen accepted. The fraction of a beam lost by scattering per centimeter of travel was shown by J.J. Thomson to be as given in the next expression. F is 8 pi divided by 3 times n times e to the fourth power divided by m to the second power times mu to the second power. And you can see what those letters mean. F is the fraction of a beam, n is the number of electrons per cubic centimeter, m is the mass of the electrons, e is the electric charge, n is the atomic weight, and mu is the linear attenuation coefficient. N, E, and m had to be measured and the atomic weight calculated. When these came more precise, it supported the theory with help coming from Rutherford, Bohr, and Moseley. The confirmation was remarkable. The theory on which it is based is the spreading wave theory. It assumed the scattered radiation is the radiation resulting from disturbances in the electrons, while under the influence of the electrostatic field in the primary radiation. Radiation can take place from these electrons in any quantity, is not confined to units or quanta. This is a continuous process. I found that the intensity of the radiation scattered varies little with the wavelength of the primary radiation, as expected in the theory. For heavy atoms, more closely packed electrons, it is different. Here the intensity increases with the wavelength. The heavier the atom, the more the increase of intensity. Again, as expected from the theory, since the size of the atoms becomes comparable to that of the wavelength, when the group of electrons becomes the scattering unit, with heavy atoms this is the case, the intensity is proportional to the atomic number squared. With individual electrons, scattering intensity is proportional to the atomic number, thus without the square. The conclusions of the experiments do not all agree with quantum theory. Then the center of radiation, the characteristic radiation. Each element, when transversed by X-rays, emits X radiation characteristic of this element. This is unaffected by physical and/or chemical conditions or state, and that of the primary radiation. As Stowe predicted, only primary X-ray with a short wavelength cause this phenomenon. Three series, the K, L, and M series, are known. Later we will come to the J series. Bragg, Moseley, and others showed that K and L radiation give spectra with several lines. Uniformity in the distribution of this characteristic radiation shows it is uncontrolled by primary radiation excitation. Characteristic radiation is indirectly, but not directly, caused by the primary radiation, and is dependent on some critical condition. Here quantum theory may apply. I showed the total absorption of the primary radiation are apparently independent absorptions, each with the exception of those scattering related with characteristic emissions. The results obtained from a study of the energy of the primary beam absorbed, of the energy of the characteristic radiation emitted, and of the corpuscular radiation emitted are very significant. In substances with a high atomic weight, nearly all the energy of the primary beam absorbed in association with the emission of the K characteristic radiation is re-emitted partly as characteristic X radiations, if the K series and partly corpuscular radiation of the K series. There is a relation between the intensity of the K radiation and the number of electrons emitted in the associated corpuscular radiation. The emission of one quantum of characteristic X radiation for each electron in the associated corpuscular radiation is a fact now. If N and K are the frequencies of the primary respectively the characteristic radiation, the energy of the primary radiation absorbed is N, then N divided between brackets N plus Nk, and is emitted as K corpuscular radiation, NL divided N between brackets N plus Nk is re-emitted as K fluorescent radiation. The latter together are about 88 of the primary radiation. There may be doubt that the characteristic radiation is emitted in quanta. The same energy relation, however, shows that absorption is not in quanta of primary radiation, but it absorbs the energy of one quantum of primary radiation plus the energy of one quantum of the characteristic radiation, in 1 plus Nk divided by N. X-ray is thus emitted by electrons or group of electrons or even atoms as a continuous process and in any quantity. It is emitted in quanta from atoms under certain conditions, and then Planck's law, E is hf, dus energy is Planck's constant times frequency, applies. Absorption too normally takes place in very minute quantities, very much smaller than the quantum, but sometimes the radiation is absorbed in quantities. All this seems to indicate that the quantum of radiation does not exist. The process of radiation is continuous. The quantum is a unit of atomic energy which must be absorbed in order to change the configuration of the atom, and it is radiated when the configuration returns to its initial state. It thus of necessary appears in certain processes of absorption and radiation. Recent investigations led me to the conclusion that characteristic radiation of higher frequency than the K radiation, a J series, is probably emitted by light elements. A decrease in the wavelength of the primary X-ray radiation is accompanied by a sudden increase in a particular effect measured. An increase such has been invariably found to accompany the emission of the characteristic X radiation. As with the phenomena accompanying K, L, or M characteristic radiation, an increase of the element is accompanied by a decrease in the critical wavelength of that element. Direct evidence of emission of characteristic radiation has proven to be difficult, but we hope to prove the existence after new and better experiments with the light elements. One can calculate a ratio K radiation divided K absorption energy. Its maximum value in copper is 40%, in iron 30%, in chromium 20%. There is every indication that it becomes much smaller for light elements. J absorption may be 15% for these elements. Duane and others have been unable to detect any J characteristic radiation excited in aluminium when bombarded by cathode rays. This may mean that J characteristic radiation is very weak in comparison with the heterogeneous X radiation produced in aluminium. or J radiation may only be produced in association with emission of J electrons, and these may be very few or difficult to displace. Or J emission may only be excited by an impact of cathode particles. This is not in all unlikely if the J electrons are closely bound with other electrons, etc. Further experiments alone can decide on this point. One important feature of the discovery of a J series of characteristic X radiations lies in the fact that there is no room for it in Bohr's theory of radiation as applied to K and L radiations. It may however be that a J radiation is emitted by electrons in a system of different kind, as for the instance in the nucleus itself, instead of outside it. But the association of other phenomena, an association similar to that observed with K and L characteristic radiations, suggests a close similarity in the whole process involved. Experiments on this subject are at present in progress. Well, this was a summary, of course, summarized by me. If you will the complete lecture with all the elements and arguments, then you have to follow these links. And the illustrations were taken from the article Barkla shows that X-rays have polarization, which you can find here. By the way, so far as I know, the existence of the J series was never proven. But that doesn't mean that the good man Barkla did good work, of course. Here you see what happens. Here you see an X-ray hitting an electron. The electron is oscillating and sends out a secondary X-ray. As you can see, here is the primary X-ray in red, and you see two X-rays coming out of it with different polarization, of course, in different direction. Yeah, and here you see one more time. You see it even a secondary radiation here on, and this is the difference between this. This is an unpolarized X-ray beam, and here I have a polarized X-ray beam as primary radiation, which is the cause of the fact that only in this case that you have a vertically oscillation electron X-rays and no horizontal ones. You see one more time the equipment Barkla used. This is another drawing of his experiment, and here again you see vertical secondary rays and horizontal secondary rays coming out of the tube, as said as secondary radiation, and as we have seen, that only happens when you send an unpolarized primary X-ray into the bulb. Yep. Okay, this was it. Thank you for watching. Next week we will go to the Nobel Prize of 1918.